Okay, so now let's do the multi-dimensional Newton Raphson method for the system of non-linear equations. So the multi-dimensional Newton Raphson method can be used for the system of non-linear equations using the Taylor series for more than one variables. We can write down the equations, okay, in two variables in this form. Okay, I will not go into the derivation of these equations. So this is a set of two linear equations with the two unknowns that can be solved for the values of x. So what are the unknowns? The unknowns are xi plus 1 and yi plus 1. Okay, xi plus 1 and yi plus 1. These are the unknowns, whereas all the other values, partial u over partial x, partial u over partial y, can be calculated, and then other values can be calculated. Okay, so when we if we see that there are two unknowns in these two equations, and if you remember that in the system of linear equations, when there are two unknowns, we can solve them simultaneously, and there are many methods. So one of that method is the Cramer's rule, and when we do the simplifications, then we can write their solution in terms of xi plus 1 and yi plus 1 into this format. So in this format, the denominator is common. Okay, this denominator is common: partial u over partial x, partial v over partial y, minus partial u over partial y over partial v over partial x. This common denominator is called as the Jacobian of the system. It is actually the determinant of the system. Okay, just as in the Cramer's rule, if you take if you want to take the determinant, so then you multiply this term with this term, partial u over partial x, partial v over partial y, and then minus partial v over partial x into partial u over partial x. Okay, so this is the same term here, partial u over partial v over partial x, and then it is the same term. So this is the determinant, and then on the top we have the other terms. Okay, so it is actually not very easy to remember, so therefore it's better to have these equations handy when solving the question. Okay, so let's see it with the help of the example. Newton Raphson for a non-linear system. So problem statement. So use the multiple equation Newton Raphson method to determine the roots of equation 6.19. Note that the correct pair of roots is x is equal to 2 and y is equal to 3. Initiate the computation with the guesses of 1.5 and 3.5. And just for your recall, the equation 6.19 for this. So set of two simultaneous nonlinear equations. So just apply these values into the equation. So remember that we have to take the partial derivative of u with respect to x and u with respect to y, v with respect to x and v with respect to y. So that is easy to remember. Okay, so we have two functions u and v, and then two independent variables x and y, and then we have to take their partial derivatives. So these four things we have to do it in any case, and then when we have to do these four calculations, then we can apply the initial guesses into these. So for example, if we take partial u over partial x, so it will be 2x, and then because it is x, so y is constant, so y, and then for 10 it is 0, so it will be 2x plus y, and the value of x will be applied as 1.5 over here, the value of y will be applied as 3.5 over here. Similarly for partial u over partial x, so you can see that partial u over partial y with respect to y, so this will be 0, and because this with respect to y, so it will be x, and then this is 0, so it is x only, it is only x, so x is of course 1.5. And then v, partial v over partial x, that means the derivative of v with respect to x, it will be 0 here, and then 3y square, okay, 3y square, because x is 1, x will be 1, and then this is 0, so 3y square, so it is 3 into y, the value of y is 3.5. And then v with respect to y, okay, v with respect to y, so y is 1, and then with respect to y, so it will be 3 times 2, 6y, and then of course this will be x, okay, as a constant, so 6xy, so 1 plus 6 times x is 1.5, y is 3.5, so it will be 32.5. So from this then we can calculate the Jacobian. So Jacobian will be partial u over partial x multiplied by partial v over partial y minus partial v over partial x multiplied by partial u over partial y. So it will be 6.5 times 3.32.5, yes, and minus 36.75 into 1.5, or yeah, so 1.5, so it will be 156.25. so basically we have already calculated the determinant, okay, in both, for both of these roots. So what we have to apply is the values, we have to substitute the values for xi and then over here, okay. So yeah, this is the Jacobian or the determinant for the Cramer's rule we have calculated. So the values of the function can be evaluated at the initial guesses as, because we need u naught and v naught. Why? So because you see that in this formula, okay, we need the values u and v, okay. So because we are starting from the initial value, okay, so it will be u naught, v naught, so values of u and v we need to calculate. So u naught and v naught means we will, in this function we will put the value of x as 1.5 and value of y as 3.5, and similarly for here. So here then we calculate u and v over here, okay, and then this gives us the values of minus 2.5 and 1.625, and then we can substitute the values into these two equations, okay. I have, so 1.5 minus 1.5 was xi, so this one minus u was already before calculated, and then v over y, it was also calculated before, minus vi, so we calculated before over here, yeah, over here. So and then just in these values, so this will give us the values of x and y, which is 2.03 and 2.603, 2.03 and 2.84, just substituting these values. So thus we can see that the results are converging to the true values of x is equal to 2 and y is equal to 3. So the computation can be repeated until an acceptable accuracy is obtained, okay. So maybe I can show it also on Excel as well, okay. Okay, so for the calculation on Excel, I have calculated all the necessary information. I have input all the necessary information on Excel, so just for my reference. So maybe I can start, you can start your Excel sheet in any way which you feel comfortable. So maybe I can start from I, which shows the iteration, and then I can start with the xi, okay, yi, and then ui, okay, vi, which is the value of the function. Then I can calculate ux I, which will be partial u over partial x, then u vi partial u over partial v, u yi, so this will be partial u over partial y. Then it will be you can calculate v xi, which will be partial u over partial x, and then v yi, which will be partial v over partial y, and then maybe we can calculate something more. So let's see, do some calculation so that picture becomes clear. So first iteration, and then we are taking the initial values as 1.5 and 3.5. Let me check what these values seem. Yeah, initially 1.5 and 3.5. Okay, and now I calculate the ui. So ui, for this I will take ui. So ui was x square, so 1.5 square plus xy, 1.5 times y, and then minus 10. So this is ui, so it is minus 2.5. Yeah, I remember it was the same value before. Now I calculate v. V is y, so y plus 3 times x times y square, so y square, and minus 57, so it is 1.625. okay, so next I calculate uxi, uyi, vxi, and vyi. So for this I need to be better if I take the derivatives of this, and then I can put it over here. So I have copied the partial derivatives which I need to do. So ux, this is this one, so it will be then equal to 2 times x is here, and plus y is here, so it will be 6.5. uy, it is actually equal to only x, and vx, it is 3y square, so equal to 3 times y square, and then vy, partial v over partial y, is equal to 1 plus 6 times x times y, so it is 32.5. Now maybe the next step, maybe you can calculate the Jacobian. So Jacobian is this times this minus this times this. Okay, so is equal to u into x, ux times vy, yeah, minus vx times uy. Okay, so it will be 156.125. Okay, so and then the next step is to apply xi plus 1 to calculate, and then yi plus 1. So xi plus 1 we can calculate by this formula xi, so it will be xi minus bracket ui, ui is this, times vy, vy is here, minus vi, vi is here, times uy, uy is here, bracket close, divided by this Jacobian. Okay, so it will be 2.06. And similarly we can calculate yi, which is equal to yi minus. So for yi, so it will be C10 minus then bracket vi, so vi times ux minus ui times vx, and then divided by the Jacobian, this one, so it will be 2.84. Okay, so for the second iteration, so we can set the values of the which we calculated in the previous iteration, so that is equal to this and equal to this, and for yi this is the value we can set. And now I can repeat these calculations. So in the next iteration, I can see that I am getting the values very close to the original solutions 2 and 3. Maybe we can do few more, 3, 4, okay, 2 more iterations. So in this case, I just have to drag this down to copy the calculations. So I can see that now the solution is almost exact. So where you can see that the solution has converged very rapidly in this case. So that's all for this method. So with this we have completed this topic of open methods. So for a review, so first of all we introduced with this open method, which are in contrast with the bracketing methods. So we started from the simple fixed point iteration method, and then we moved on to the Newton Raphson method, okay, and then we did the secant method, and then modified secant method, and then the comparison of the false position in the secant method, modified secant method, of course, and then the did the topic of the multiple roots, and then in the multiple roots we applied the modified Newton Raphson method, okay, and finally we did the system of nonlinear equations, first with the method of the fixed point iterations, and now lastly by the multi-dimensional Newton Raphson method. So next we will start the topic of polynomial equations, the solution of polynomial equations.